Alright, this video is about ions and their electron configurations. Alright, and so a positively charged ion is called a cation, and it's where they lose electrons. And then a negatively charged ion is called an anion, and that's where they gain electrons. Because remember, electrons are negative, and so if it gains electrons, it's going to become more negative. If it loses electrons, then it's going to have more protons than electrons, and so it's going to be positive. Alright, so if we look at lithium, lithium has 3 electrons total, right? And so the first 2 are going to be right here. And then the last one is going to be out here. And so it has, this is where n is equal to 1, and this is where n is equal to 2. Remember, that's the principal quantum number. So when we do the electron configuration for that, it's 1s2, because there's 2 electrons where n is 1, and then there's 2s1. All right, and the Lewis dot structure, it only deals with the valence electrons, and so we would just write it Li and then put a dot next to it. All right, and so lithium likes to be +1 because it's going to lose, it would have to gain, how many electrons would it have to gain to fill its outer shell? Atoms will either lose all of their valence electrons or fill the outer S and P electrons. And so in order to fill its outer shell, it would have to gain 7. It's not going to do that. It's just going to lose this electron. And so if it loses its valence electron, this one right here, then it becomes Li plus 1. And the electron configuration for that would simply be 1s2. All right, magnesium. Magnesium has 12 electrons total, and so there'll be 2 in the first energy level. There'll be 8 in the second, and then in the third energy level there will be 2. Okay? And so this right here is where n is equal to 1, and this is where n is equal to 2, and this is where n is equal to 3. And if we look at the electron configuration for magnesium, we have 1s2, 2s2, 2p6, 3s2. And so you can see right here, in the first energy level there's 2 electrons, in the second energy level there's 8 electrons, and in the last energy level there's 2 electrons. And so its highest energy level is where n is equal to 3. And so that's its valence shell. If it was going to fill the S and P of its valence shell, it would have to gain an extra 6 electrons. So it's not going to do that. It's just going to lose its outer 2. And so magnesium likes to be 2+. And so the electron configuration for magnesium 2+ is where it's lost those 2 electrons. And so it would simply be 1s2, 2s2, 2p6. And the Lewis dot structure for magnesium, not the ion magnesium, but just magnesium, is going to be Mg, and it has 2 dots. So it'll lose those 2 electrons to become that. All right, Next, we're going to do phosphorus. No, I'm sorry. Oxygen. Okay, and so oxygen has a total of 8 electrons total. There'll be 2 in the first ring, and so then there'll be 6 in the next ring. And so oxygen can either gain 2 or it can lose 6. And so in this case, it's going to gain 2 electrons. All right, and if it gains 2 electrons, then it's going to become 2 negative. And where are those 2 electrons going to go? So let's write the electron configuration for just oxygen first. That would be 1s2, 2s2, 2p4. And so it's going to have to fill up the s and the p of the outer energy level. So those 2 electrons go into that 2p orbital. And so it's going to be 1s2, 2s2, 2p6. And the Lewis dot structure for just oxygen is going to be an O, and then we write 1, 2, 3, 4, 5, 6. And so if it gains 2 electrons, it turns into that. Okay, and then the next one we're going to do is phosphorus. And phosphorus has 15 electrons. And so the first ring is going to have 2. The next ring will have 8. And then the last ring has 5. You can't write over there. Put it right there. Okay, and so it'll look like that, right? And so phosphorus is valence shell for the Lewis dot structure, because remember, Lewis dot structures are only the valence electrons. You'd go 1, 2, 3, 4, 5. And so you have to put 1 on each side of the 4 sides of the square, and then you can go back and pair them up. And the electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. And so this one can either lose 5 or gain 3. And so it's going to gain 3 electrons. And so it becomes p3 minus. And then it's going to look like, so they're going to have to go into the p subshell. So it'll be 1s2, 2s2, 2p6, 3s2, 3p6. So if this gains 3 electrons, it turns into that. So as we look through the periodic table with these main group elements, remember we looked at lithium, and then we looked at magnesium, and we looked at oxygen and phosphorus. So group 1A elements are going to have a +1 charge. And group 2A elements are going to have a +2 charge. Now aluminum is going to be +3, okay? And then 4A elements will be plus or minus 4. 5A elements will be -3. 6A elements -2 because they're going to gain 2 electrons. And 7A will be -1 because they're going to gain 1 electron. Now when it comes to these elements down here, they're a little different. All right, they don't follow the same rules. They're called transition metals, or at least half of these are, and that's because they transition. they have different oxidation states, okay? And then these guys down here can vary as well. All right, so there you can't determine their normal ion state just by looking at the periodic table. You can kind of guesstimate, but it's not as easy. Okay, so we're going to look at some examples of those. And the first one is technetium. Technetium is right here on the periodic table. It has 43 electrons, and so I'm just going to look at the electron configuration of plain technetium, but I'm going to do the abbreviated version, so I'm going to use krypton as its noble gas first. So I'm going to put krypton in brackets, and then from there I'm going to start at, let's see, this is 1, 2, 3, 4, at 5s2, and then I have 4d, 1, 2, 3, 4, 5. Okay. All right, so if we wanted to do technetium 2+, where would it lose its electrons from? We know it has to lose it from its outer shell, its outer energy shell. And so remember, if this is your atom, and this is where N is 1, and this is where N is 2, and this is where N is 3, and this is where N is 4, and this is where N is 5, then this shell right here is here, and this shell is up here. So it's going to lose it from its outermost shell, this shell. So it's going to lose it from here. And so if it becomes 2+, the electron configuration is going to be krypton 4d5. Now, if it becomes 3+, it has to lose one more. And so then it can come from here. And so technetium 3+ is going to be krypton 4d4 because it lost an extra one. It lost the 2 from right here, and then it lost 1 from right here, and that makes it 3+. All right, 2 more. We've got antimony, and so again, I'm going to use krypton as my noble gas because antimony is right here. So I've got krypton, and then 5s2, 4d10, 5p, 1, 2, 3. Oops. All right, so if it loses 3 electrons, it has to lose it from its outermost shell. Well, this right here is its outermost shell, and so it's going to lose it from the P before it loses from the S. And so the electron configuration for antimony 3+ is going to be krypton 5s2, 4d10. And then if it loses 2 more electrons, so it has to lose all 5 of these electrons right here, it'll just be krypton 4d10. All right, and then to define a word, an isoelectronic species. Isoelectronic means they have the same electronic structure, so they'll have the same electron configuration. And so if we look at sodium plus, sodium is right here. And if it loses an electron, it's going to become just like neon, right? Its electron configuration is going to be 1s2, 2s2, 2p6. And if we look at fluoride, it's got, here's fluorine, and it's going to gain an extra electron, so it's going to be just like neon. So it'll be 1s2, 2s2, 2p6. And neon is 1s2, 2s2, 2p6. And so all 3 of these are isoelectronic. Now, don't get that wrong. Sodium, fluorine, and neon are not isoelectronic, but the sodium ion and the fluorine ion and neon are isoelectronic with each other.